All right, everybody, we have one more integration technique to talk about. Not integration technique, but numerical integration techniques, ways to approximate the value of a definite integral. We talked about Riemann sums and the error associated with using those. We've talked about trapezoid rule now, and that provided us with a different scheme that, with a few small changes, led to an easy-to-use formula that we could then get a better result on average with. And we're not done there. There's going to be one more extension that we use. You might be able to gather from the badly drawn thing behind me that what we're going to get into here is called Simpson's rule, although it has nothing to do with the show. So let's get into that. Let's talk about Simpson's rule. And how does it extend? It extends basically, trapezoid rule is to Riemann sums what Simpson's rule is to trapezoid rule. So Riemann sums approximated a function essentially by a piecewise constant function to give us rectangles that we would find areas of. But trapezoid rule doesn't use constant functions, it uses linear functions and connects the dots that way to get a better representation most of the time. So let's fill in those blanks and actually get this started here. So yeah, Riemann sums give an estimate using a piecewise constant function, as we see, and trapezoid rule a piecewise linear function. So it begs the question, why not go further? Maybe there's a way to use a collection of, here, let me zoom in a little bit here, of quadratics to provide an even better approximation. And that is what the motivation is behind what's known as Simpson's rule. So I want you to consider this integral. This is a definite integral from a to b of some f. So what we've been talking about for the last couple of lectures. F is continuous on that function a to b. We discretized into three equally spaced nodes. We're going to call them x0. That's the a, the left endpoint. x2 equals b, so that's the right endpoint. And x1 is going to be the one in the middle. So what is the average of those two? Well, it's going to be a plus b over 2. So the midpoint of the interval. Okay, so quadratic. Let's think about how we could create a quadratic. We have the tools. We just have to go back about a month or a month and a half to think about what we used to be able to find a quadratic. And we have, interpolating polynomials to do this, right? We can find a Lagrange interpolant that takes 3 points, i.e. x0, x1, and x2, and interpolates the curve f of x at those 3 points. That's going to give us a quadratic function in general for 3 points, and that's what we're going to use. We're going to find the quadratic that passes through the curve at those 3 points. And finding that quadratic is no harder than finding the Lagrange interpolant, and that's what the exact exercise is. So we have an x0, x1, x2. Why don't we use the same notation for our interpolant and use L0, L1, and L2. So L0 is going to be, if you remember, x minus the other points, so x minus x1, x minus x2 over x0 minus x1, x0 minus x2. L1 is going to be x minus the other points, so x0, x minus x2 over x1 minus x0, x1 minus x2, and then L2 is going to be x minus x0, x minus x1 over, oops, sorry, I don't know why I got that little tick mark there, but x minus x1 over x2 minus x0, x2 minus x1. Okay, so we have these things. They're a little bit awkward to calculate, but we've literally done this before. It's not that hard. We have code that we can use to find these things, so that's cool. And then the p of x, the actual interpolant that we're looking for, is going to be given by the right number times the L0 plus the right number times the L1 plus the right number times the L2. What are those right numbers? Well, remember, those are the basis functions, the L0, L1, L2. They need to be lifted to the right y values. And those are going to be f of x0, f of x1, f of x2. So let's write those down. So it's f of, where's my cursor? F of x0 times L0 plus f of x1 times L1 plus f of x2 times L2. So something like that. That's going to be a quadratic. And the reason it's a quadratic is because, well, fx0, fx1, fx2, those are just numbers. And you can see that each one of those L0, L1, L2, those are going to be quadratic functions. So if you add them all together, you're going to get a quadratic function. If the resulting quadratic is a good approximation of the curve, the associated area under it should be a good approximation of the true area. And that's really what it comes down to. That is the area which is given by the true integral, the true definite integral, a to b of f of x dx, is well approximated by the area under our Lagrange interpolant, the p of x that we just constructed. So that's kind of how this is going to be constructed. You can actually do this integral. That is, you can take all three of those expressions and find a general formula for this integral. And that's what we would have to do every time if it didn't lead to a general formula. But it leads to a general formula, and that's what we're going to work with instead. I will leave that as a whole exercise. If you really want to go into it and take that sum of three different quadratics and work it all out, you do that. I'll make it a for you to try question if you really want to. However, if you do all that work, this is what you're going to get to. The area is approximately equal to, if you do that integral, you get this right here. You get x2 minus x0 over 6, which seems kind of interesting, but that's just what it turns out to be. And then you get f of x0 for f of x1 and f of x2. This formula is equal to this integral. And this integral approximates the true area. And that's where this comes from. That's why it works out well. However, one thing that's really nice is when you have evenly spaced nodes. The nodes are the points, right? The nodes are the points that determine the subintervals. The subintervals, if those are all the same size and the nodes are equally spaced apart, then you can actually boil this down to a little bit of a nicer looking formula, right? You can instead consider a uniform subinterval width of h. So that's if all of the different subintervals are width h, then you can write this instead. And most of the time, that's what we're going to be working with. It's weird to try and talk about changing subinterval size, but you can. And there might be some places where that's actually really useful. Maybe if the function changes really, really quickly in one region, you want to go to a smaller subinterval size so you can try to capture that rapidly changing behavior. But for most of the time, and for the formulas that we'll develop here, we're going to mostly consider uniform subintervals. So I want you to concentrate on this formula right here. So if you do that, then you can take this quantity right here, boils down to be an h over 3 if you sub in the right things. And that's just thinking of, we would take, what is the h size? The h size is generally going to be the b minus the a over the number of subintervals. And if we have 3 nodes, that's 2 subintervals. So that's why there's a factor of 2 difference here. If you work things out, you get an h over 3. And yeah, this last thing, this is known as Simpson's rule. And it's named not after Homer, but after Thomas Simpson, who used this in the 1700s to do some approximating techniques. And we're going to use this to approximate the value of this definite integral. Also a special function. We cannot actually find an antiderivative for this thing, but we can approximate this integral. So we're going to use Simpson's rule to approximate the value of sine of x over x. We have, in general, for Simpson's rule, we have exactly 2 subintervals and 3 nodes. So let's start by writing that down. 3 subintervals, 2 nodes, I'm silly. 2 subintervals and 3 nodes. Let's try that again. And those nodes are equally spaced. I'll say we assume that. Nodes, and we're going to list them right here. So we have 1 to 2. These are our domain of integration. If I want to divide that into exactly 2 subintervals, it's going to be 1 to 1.5 to 2. There are my 3 nodes. So x0 will equal 1, x1 will equal 1.5, and x2 will equal 2, with, of course, our h being 0.5. And it's just going to be a matter of adopting what we have above. So using the formula for Simpson's rule, the area is approximately equal to, or this integral is approximately equal to, and it's going to be, let's see, h over 3. That's 0.5 over 3. And then we take f of 0 plus 4 f of, not f of 0, f of 1. That's our first node. F of 0 would be pretty tough. We have a sine of 0 over 0. That would cause some issues, wouldn't it? So we have f of 1, and then 4 f of 1.5, and then f of 2. And so that turns out to be, yeah, remember we're just working with the integrand here. That's what the f is. So this here is our f. And so subbing this in is really just a matter of sine of 1 over 1 plus 4 sine of 1.5 over 1.5. Just a reminder again, just because it seems to come up all the time, if we're using trig, we're talking radians. So if you're doing these calculations, I expect you to be working in radians. That's just a thing we have to be able to count on at this point. Unless you're doing like, angles in grade 12, or you're using some like applied mechanics problems and stuff like that. Like we're using degrees and stuff. This is in radians. This works out, if you work it out, to about 0.65935 or so. And the true value, just so if you're interested in seeing how good of a job this does, the true value is about 0.65933. So, right, all we've done is carve this into 2 subintervals and fit a single quadratic through those. I don't know what it looks like. Maybe it looks like this. Maybe it looks like that. I'm not sure. But we've got one quadratic. We found the area under that quadratic, and holy cow, we're correct to 1, 2, 3, 4 decimal places. It's pretty incredibly powerful. So that's the basics of Simpson's rule, and it's not hard to use. It's a bit of a different approximation. It's got a different formula than trapezoid rule, but it tends to do a better job, and it tends to do it tends to converge to 0 more quickly than both Riemann sums and trapezoid rule. So even if it doesn't do a better job at first, as that h decreases, the error should decrease much, much more rapidly than either of the other methods that we talked about. And it will, on average, become much better of an approximation as that step size, as the subinterval width gets smaller. So what if we want to go more than 2 subintervals? That's what's called a composite Simpson's rule. We'll typically just call it Simpson's rule, understanding it to be applied to endpoints rather than 3, because, I don't know, it's not that hard to remember. If you have more than 3 nodes and more than 2 subintervals, if you want to apply Simpson's rule, you need a different formula, because the one that we talked about above only applies if you have 3 nodes and 2 subintervals. So we have a couple of considerations to make. The idea behind this is interesting. How do we do this, right? Imagine you have multiple nodes in play. So suppose you know that your curve has to go through, say, these 5 points, right? What we did for the first one was we just had 3 points. So we could take the parabola that goes through these 3 and say, oh, hey, that was a pretty good parabola. I'm just going to say that was a freehand parabola, first shot, no erasing. Look at how beautiful this thing is. Come on, I want to zoom into this. Oops. Sorry, I was just very excited. I want to show, that's a beautiful parabola. Anyway, just gonna go back to what I was doing before, instead of just showing off my prowess with the drawing tablet. But in any case, what we just did was calculate the area under that. And that's cool. That's Seems like, sure, it could do a good approximation if you know that the curve goes through those 3 points. But how would you extend this to have more points, right? You would want to take this set and be able to find the area under this set of 3. But the idea is that we're going to kind of daisy chain on another 3. The last one, though, like this node, becomes the first node of the next 3. And the next parabola is going to be this parabola. That, let's see if I can do as good of a job. Oh, no, definitely not. Oh, definitely. Ooh, not nearly as good. Let's try that again. This is probably better. This is definitely better. That looks like a parabola that goes through those 3. And see, you would then take this area and you would add it to this area. And that is generally the way that it would work. There's some interesting things here, right? It's kind of like trapezoid rule in that there's some sort of weird double counting that happens in the calculation, right? The last node of the first set of 3 becomes the first node of the next set of 3. And so if it was involved in a calculation over here, it's also involved in the next calculation, and that's going to have to come into play a little bit. So that's one thing we're going to have to think about. Another thing is, this isn't working unless we have an even number of subintervals, because I need 2 subintervals necessarily to draw a parabola over them, right? I need sets of 3 points. We know this from our work earlier. And without having sets of 3 points, I don't get a parabola. So if I'm to do this, I need to have a set of 3 points. And then if I were to have the next set of 3 points, with the last one being the first, that would need 2 more points beyond that. So I need to have like 3 points, 5 points, 7 points. I need to have an odd number of points defined in the subintervals, an odd number of nodes, and therefore an even number of subintervals. So a couple of interesting intricacies here, right? So let's fill in some of these blanks. Each subsequent set of 3 points needs to be considered at a time, creating a polynomial that lies above, what goes here? Oh, 2 subintervals, each one, exactly. Each parabola has to exist above 2 subintervals, as we saw. We will consider only the case where we have an even number of subintervals, as I said, defined using an odd number of points defining them. That makes an interesting formula, because the original one had this h over 3, and then 1 of the first, 4 of the second, and 1 of the third. But then the 1 of the third becomes counted again. So that's interesting. If we had 5 points, I would have a 1, 4, 1, and a 1, 4, 1, but the second one's counted twice, so then I get actually 1, 4, 2, 4, 1. I don't know why I'm being musical here, but it helps me remember. I don't know. Sorry if it's irritating, but whatever. Rather than deriving it from scratch, which can be done, I think that I've done a pretty good job of explaining where it comes from. The whole thing, including the integrations from before, are extremely tedious. So it's better, I think, to explain it in this way, in a more loose sort of way. This is all presented formally. The A and the B are the left and right endpoints. We want an even number of subintervals and so on. We continue in this chain as I talked about. Here's what it is. You ready? This is the formula. It goes left endpoint slash first, the A value, the left bound of the integral, gets a 1 as a coefficient. That's a 1 f of x0. The right endpoint, the right bound of the domain of integration, the B, the xn, that gets a 1 as a coefficient. In between, we go 4, 2, 4, 2, 4, 2, 4, 2 until we're done, until we're at the right endpoint. And then we end with a 4 and back down to 1. So really interesting. Probably the most interesting formula we'll do all semester. It's kind of fun to use as a result because it's not actually that hard to implement. But it makes sense, I think, when you think about it. And you think about like combining, 2 calculations at those nodes that connect to subsequent parabolas. You can write this in terms of summation notation. Don't do it. I think it's easier to remember singing a song about 1s and 4s and 2s and stuff like that. But this is what it looks like. I said right here, it's somehow less attractive and not as instructive. This is like, I don't know, was gonna make a joke about like, I don't know, feeling beautiful by day and then waking up in the morning and looking in the mirror and being like, holy cow, I need help. Um, you could be very beautiful and yet very ugly depending on the time of day or how you present yourself. And but we're all beautiful here. So anyway, this is what it looks like in terms of sums, and you can see, right? There are certain terms with a 4 in front, there are certain terms with a 2 in front, there are the basic endpoints with just a 1 in front, and the whole thing is multiplied by h over 3. So definitely an interesting formula. Again, I want to emphasize it's not that hard to use. You just got to jump in and do it. So that's what we're going to do. Use Simpson's rule to approximate the value of the error function at 1. Let's remember one more time what that error function was. It's the one special function I wanted you to be responsible for, and it was this. So the error function at 1 was equal to 2 over root pi. The integral from 0 to 1, the 1 here goes with the 1 up there. So that shouldn't be a surprise at this point. Error function at x puts an x up there. And then it's e to the minus t squared dt. So let's remind ourselves of that. And then let's look at the problem to make sure that Simpson's rule can be applied. Hint, it can be. Because we have 4, an even number of equally spaced subintervals. Cool. If we're doing 4 equally spaced subintervals and we have a domain of integration that goes from 0 to 1, let's think about that for a second. So 4 equal subintervals. That means that our h is going to be, okay, we have to take the difference. So we have to take the length of that domain of integration and divide it into 4 pieces. So it's going to be h is 1 minus 0 over 4. So it's going to be 0.25 or 1/4, right? That should make some sense to you. That means that our 5 nodes that we get are x0 equals 0, x1 equals 0.25, x2 equals 0.5, x3 equals 0.75, and x4 equals 1. Going across that domain of integration from 0 to 1 by steps of h equals 0.25. Okay, the error function also has this 2 over root pi out front, so let's not forget it like we did in that. Same thing with that last. I think the last lesson had an example in trapezoid rule where we had to also multiply a result by 2 over root pi, so that's fine. So the error function at 1 is approximately equal to, using Simpson's rule, 2 over root pi times the value of the integral. And if we use that formula, we have an h over 3, that's 0.25 over 3. And then what we want to do is take 1 as a coefficient of the first, plus 4 f of 0.25, plus 2 f of 0.5, plus 4 f of 0.75, plus f of 1. And there's the 1, 4, 2, 4, 1. Okay, so we can collapse this a little bit. 2 times a quarter is 50 cents. So we're going to get here 0.5 over, and then 3 root pi. And our function that we're dealing with, this is our f right there. It's going to be f at 0, so e to the minus 0 squared, plus 4 e to the minus 0.25 squared, plus 2 e to the minus 0.5 squared, plus 4 e to the minus 0.75 squared, and then plus e to the minus 1 squared, just like that. That's what it comes down to. And if you work this out on a calculator, or, you know, I don't think you can do this using your brain. I don't know. I can't do e to the minus 0.75 squared, but maybe you can. You get about 0.84274. And the actual value, which again, it's funny, I say actual value, but really this is just a value that's been determined numerically to like incredible precision by, you know, computers and stuff. So it's just done a better result. But we can say that the true result is actually about 0.84270. So it does an excellent job. And that's how it works. Hopefully that makes some sense. Hopefully the formula, while interesting, is just kind of fun to use and not too bad, no matter how hard the function might be, right? So that's kind of yeah. I have a couple little notes that I want to say about this process to wrap things up here. So let's do that and wrap things up here. So, assume that we're using a numerical integration scheme to approximate this integral with a uniform partition and so on. I want to have a couple of little notes on the error. The error certainly shrinks to 0. No matter whether you use Riemann sums or trapezoid rule or this new Simpson's rule. It's just how quickly the error tends to shrink to 0. The error decreases on different orders. That's why we talked about the whole big O notation at the start. Riemann sums, using right or left endpoints, produce error that is big O of h, while trapezoid rule produces error that is big O of h squared. You could probably surmise that when you look at the error formulas from the last two things. Simpson's rule has its own error formula that we could use. I'm not going to state it here, but you could look it up if you like. But its error is significantly improved. It is on the order of h to the 4. And if you think about how a quartic function, an x to the 4 function, comes in to the origin, it does so extraordinarily quickly. If you take a number less than 1 to the power of 4, it decreases very, very quickly. So that just gives you an idea of how much better this method tends to be when you use it. So a couple of last things here. There are quadrature, that remember was a kind of old-fashioned name for numerical integration. There are these methods that go beyond even Simpson's rule. There's more information in your text and in all sorts of online sources if you want to look. But I thought this would give you a really good start into some of the major players in numerical integration. And it's possible to extend these schemes to include varying space between nodes. And that's kind of as I say, rather than having a single value for h, you might have one that varies the values of h. And that sort of extension is useful to get a more accurate estimate in regions where the integrand is changing extremely quickly, where maybe you want to slow down, grab a little bit more data, and get more careful approximations where the function might be doing something a little wacky. Yeah, that's what I got. So hopefully you were able to follow okay. This takes us to the end of our section on numerical integration, which I think is really fun. We are coming toward the end of the course. We only have a few lectures left. I am supposed to do something regarding matrix methods in this course for solving systems, algorithms for reducing matrices, stuff like that. So we're going to do a couple of little things like that at the very end. MATLAB is really useful to deal with stuff like that too. It thrives in vectors and matrices and handling that sort of math as well. So that will be there as well. Yeah, we're almost here at the end of the course, and I really appreciate you taking the time out, watching these videos, following along, and asking questions where needed, because that is super, super important when you're gathering information for this course just virtually. So I want to say, I'm looking forward to that last week, but take care of yourselves. Until next time, everybody, bye for now.